Assalamu alaikum. We know when electric current is passed through a coil, it produces magnetic field. Therefore, the magnetic flux of the magnetic field is linked with the turns of the coil. When electric current passing through the coil changes, the magnetic flux linked with that coil also changes. When the magnetic flux linked with the coil changes, it produces an EMF in the coil. We call that EMF as self-induced EMF, and the phenomena is referred as self-induction. In this video, we will discuss about self-induction. For that, I take an inductor or a coil which is connected to a cell. A battery is a battery which is in turn connected to a rheostat through a key. This is the rheostat RH. Here this end of the coil is connected to another end of the rheostat. So with the help of rheostat, we can vary the current flowing through this coil. Just got a number of turns. Now suppose I pass current through this coil. By doing so, what happens? It produces magnetic field around it. This magnetic field will appear something like this. This magnetic field will have magnetic field lines. It appears here. No? And if it is a solenoid, then it will produce a uniform magnetic field along its axis. This magnetic field will be acting in this direction. Okay. So from this it is clear that the magnetic flux is linked with this coil itself. If it consists of a number of turns, then the total magnetic flux linked with this coil is given by multiplying the magnetic flux phi with the total number of turns. So this provides the total magnetic flux linked with this coil due to the flow of a current through it. Okay, and this magnetic flux linked with the coil is found to be directly proportional to the current flowing through the coil. The current flowing through the coil is taken as I. To do so, I remove this proportionality. When I remove this proportionality, I have to include a constant along with equal to sign. This constant is called as constant of proportionality. Right? I name this constant of proportionality as L. It is named as L. And here L stands for self-inductance of the coil. It is also referred as inductance. Now from this, L value can be obtained by cross multiplication. Now bring I this side, it will divide. I rearrange this. L is equal to N 5 upon I. This is the expression of self-induction or self-inductance of the given coil. Now suppose the current which is meant to pass through the coil is equal to 1 ampere. If I equals to 1 ampere, then this equation, this will become L equals to N5. Okay. This clearly shows that the self-inductance of a coil having n number of turns is equal to the total magnetic flux linked with it when we pass 1 ampere current through it. Okay, so this is one definition of self-inductance or self-induction. Now we know very well, whenever there is a change in a coil, whenever there is a change in the magnetic flux linked with the coil, it induces an EMF. So the induced EMF in the coil is taken as epsilon. And it is found to be equal to the rate of change of magnetic flux linked with the coil. And the magnetic flux, total magnetic flux is N5, change in magnetic flux with the time. This we have obtained from Faraday's law of electromagnetic induction. Okay. Now we know N5 is nothing but Li. We know N5 is Li. It's mentioned here. Now I'm going to substitute this one in the other equation. What I'll get if I do so? Substituting N5 value. I get this. Epsilon equals 2 minus d of Li divided by dt. Now here L is a constant, so it is taken out. Minus L di upon dt. This is what we obtain. Here, what does this minus sign represent? This minus sign shows that the EMF induced in the coil due to the change in the current always flow in a direction to oppose the cause. Clear? So we have a minus sign here. No? Rewrite this one in this manner. Here, L value can be obtained by bringing this part here, the left hand side. Epsilon along with minus sign and bring this part, epsilon upon minus di upon dt is what I obtain. Okay. So the next step, this can be rearranged and written in this manner. L is equal to minus epsilon upon di divided by dt. Okay. Now suppose the rate of change of current is equal to 1 ampere per second. Then if di by dt is equal to 1 ampere per second, then the above equation on substituting this value becomes equal to minus epsilon. So L value becomes equal to minus epsilon. So this clearly shows that the self-inductance of a coil is equal to opposing EMF when 1 ampere, when the change in the current, the coil is equal to 1 ampere per second. Got it? So these are two different definitions of self-induction. Now, how do we measure the self-induction? Let me tell this to you. Unit of self-induction. Self-inductance, okay? Here, self-inductance is measured in Henry. It is Henry. It's Henry. Henry is the representative letter H, capital H. And here it has got the alternate units as well. What are they? Let me write those alternate units. The first alternate unit of self-inductance can be obtained from this equation. Here we have 5 divided by I. So 5 is represented in Weber. It's measured in Weber, and the current is measured in ampere. So by keeping this in mind, unit of L can be written as Weber per ampere. Weber per ampere. Okay. In a similar way, if we use this expression, then L value can be written as minus epsilon. I take it to numerator, it becomes dt upon di. So by keeping this in mind, unit of L can be written as, here EMF is measured in volt. So we write a V for volt. Then here time is measured in second. And we have current in the denominator, which is measured in ampere. So ampere per ampere. This is the alternate unit of L. So one can also measure self-induction or self-inductance in these units: Weber per ampere or volt second per ampere. And here the dimension of self-inductance or self-induction is this. Here the dimension is L square T power minus 2 and A power minus 2. This is the dimension of self-induction. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put a question in the comment section. Thanks for watching.